here's a general overview. I bet most of you guys know that the very first one is linear because it's a line. This next one, this is called a square root function. I'm just going to write square root. This next one is cubic. I'm just going to write it at the bottom right here. And then the V shape is always absolute value. Good job. And then this one is the exact copy of that one, but sideways. So if they're exact copies but sideways, then it's an inverse. So that's a cubic function or a cubic root. And then, I cannot trace this continuously without lifting up my pencil. So that means if it's discontinuous, it has discontinuities. It looks like these have infinite discontinuities. The only way infinite discontinuities exist is from a fraction. And fractions are rational numbers. So that's a rational, and look, I used red on purpose because this is my asymptote pen. That's a rational function. What else we got? Oh, we got our favorite down here. I know that's called a quadratic. And then, you know what? This is a log. And that's all you need to know. We're not worried about that until after spring break. Just know that's a log function, and we'll talk about that later. Not this grading period, not even this semester, not even this year. It's going to be next year. This is a constant. And this is a GIF. And that really stands for greatest integer function. Greatest integer function. And guys, no decimals. I got these gaps occurring in that little thing. No decimals. Also, I would just like to bring to your attention, this is also what calculus calls a step function, because they look like little steps, but the formal term really is greatest integer function. All right, those are the names. Now let's break down some characteristics for this stuff. Back to the top. I am going to talk about this one, which is y equals x. I am going to talk about this one, which is y equals x to the third. What else am I going to talk about with this group? I'm going to talk about this one. This is y equals the cube root of x. And those are the three I'm going to talk about together. And the reason why I'm talking about those three together is because they're all odd. And I know they're all odd because they have opposite end behavior. So look, I personally, I hate writing this. Like, this takes so much time. And I know it's formal, and I really do have to write that stuff on tests and quizzes, I do. But let me just show you a little shorthand for the end behavior. So I'm just going to write EB right here. And I know the left arrow is down. And I know the right arrow's up. Have y'all seen that before? Has anybody seen that little short abbreviation? Yes, no? Do you know what I'm talking about here? Negative infinity is going down. My positive infinity arrow is going up. This has opposite in behavior because the equation is odd. That's 2x to the first power. First power is odd. Let's look at this. I'm skipping that on purpose because this one's very similar. This end behavior is down on the left, up on the right. That end behavior is also opposite because the equation is odd. Same with the cubic root. That root is odd. If that root is odd, then my end behavior is opposite. Down on the left, up on the right. So the end behavior is opposite because the equation is odd. One more thing, all odd functions share in common. Guys, what's the domain of this? Sure is. What's the range of this? We're going to copy that right here and right here. So domain and range. All real numbers, but you know how pre-cal is. You have to write it in interval notation. And we're going to write it 2 more times. We're going to write it for the cubic function and then for the cube root function. So linear gets it, cubic gets it, and cube root gets it. Okay. Now I'm going to talk about other graphs together. Now I'm going to talk about graphs together that have the same end behavior. And the only 2 graphs on here that have the same end behavior are these 2. Your absolute value and your quadratic. Those are the only ones here considered even. So remember your absolute value. Don't forget to draw those vertical bars. Remember for your quadratic, it's y equals x squared. So the end behavior for your absolute value, look, up on the left, up on the right. We're going to draw 2 up arrows that are the same. Absolute value is considered even because of the shape of the graph it makes. Now, your quadratic, it's so much easier to see that it's even because it's raised to an even exponent. So this end behavior is up, up for both arrows. It has the same end behavior because the equation is even. Now, there's one more thing they share in common, the domain. The domain for quadratic and the domain for absolute value is negative to positive infinity, but not the range. It doesn't go down forever. Guys, what's the range for both of these? Do you know it? Yes. 0 to infinity. But y'all, let's put a bracket on 0 like this because we get to include 0. And then before we move on, just because I know where we're heading, all even and odd functions have negative to positive infinity for domain. All real numbers. You can plug in anything you want in an odd and even function. You can get any range you want for odds, but not for evens. All right, now we're going to talk about the rest of these crazy graphs. The square root function, guys. Let's go back up to the top. Guys, this is going to be the square root of x. The domain for this, now I can't really consider it odd or even. The domain for this is going to be including 0 to infinity. And my range matches this. This is 0 to infinity. Remember, you can't have negatives in a square root function. And then, before I drop my green pen, before I go to my asymptote pen, let's talk about this constant. Let's go down here. So guys, this is y equals c. C stands for a constant. All numbers are constant because they never change. So this is y equals 2. 2 is constantly 2. 2 is never going to be anything other than 2. That's why it's called a constant function. Now, for the domain, y'all, it is negative to positive infinity. Like, I could put any x value I want. But the range, I'm stuck. Whatever that constant is going to be the range. All right, so back to my red pen, because I'm going to this red graph, because there's discontinuities on this rational graph. Remember, rational means you can write it as a fraction. Here's the equation. This is y equals 1 over x. Oh, what can x naught be in the denominator? In fact, let's label these asymptotes. X equals 0 right there. Y equals 0 right there. It is so easy to write the domain and range after you write the asymptotes. Because when you write the asymptotes, you just talked about what you cannot have. So, the domain for this is negative infinity all the way up to 0. But as soon as you pass 0, then you can put in any positive number you want. Same for the range. So for the range, negative infinity, see how it goes down forever? All the way up to where y equals 0. Look, we even wrote it for y. But as soon as we pass 0, again, you can have any positive output you want. Last but not least, the domain and range here. So guys, if you notice, there's steps here. And the reason why there's steps is because we want all of our outputs to be integers. And integers is just a fancy word for no decimals. Whole numbers, whole negative numbers. That's why it creates those flat little steps right there. So when it comes to domain and range on this, I'm not going to ask you to write it because it would be set builder. Just remember that outputs are always integers. Outputs, which is range, are always integers. Are there any questions on this?